Thank you very much. This talk is going to be about DNS and privacy, about how the current design of the DNS compromises users' privacy, what's being done about it, and where we are today. I work for a consultancy called Synodon, but I also want to thank some of the other people who've been contributing towards the DNS privacy project. So I'm also getting funding from Salesforce and through the NLNet Foundation, and there are a whole variety of other players in this space, but I just wanted to thank them specifically. Okay, so what I'll do with the talk is I'll start with the problem, why internet privacy in general is an issue, which I think we do all appreciate, but very specifically where DNS fits into that. I'll talk about what's happened mainly through the DPRIVE working group over the last 3 to 4 years to change the way the DNS protocol works to try and address these problems. And I'll talk about where we are today with tools and deployment. I'm going to start with a couple of slides, and I want to credit Daniel Cohn-Gilmore of the ACLU with these slides. He and I have jointly presented on this, and I've shamelessly stolen some of his lovely pictures and ideas here. One of the main concepts that he always wants to get across is why do we care that our activity on the internet is surveilled? And one of the major reasons is that surveillance can be used as social control by many organisations. So this picture here is of something called a panopticon, which is a jail that was designed in Victorian times. And the idea was a single guard on a central tower could have visibility of hundreds of prisoners' activities with very little effort expended. And it makes a good parallel for the way the internet works today, in that there are a handful of agencies who can vastly see your activity on the internet through surveillance at a few points. And because of the scale of machine learning today, those small set of individuals and organisations can know a vast amount about what individuals are doing on the internet. One counter-argument that's given against this is, well, I'm a law-abiding citizen. I don't have anything to hide. I don't mind being surveilled. But there's been some really interesting research done lately to show that we're social creatures, and that really isn't actually true. If you take people with that standpoint and you put them in environments where they think they might be being surveilled or they're not, and you ask them certain questions, what you see is that depending on whether they think they're in the minority with that answer, their answer will change depending on whether you tell them they're being surveilled or not. And so this is really driving to the heart of the fact that surveillance does matter. It changes people's social behaviour, which in modern democracies is a very frightening thought. And as I mentioned, DNS fits into a bigger picture here. Now, you heard this morning the fact that in TLS, the SNI, the name of the server that you're contacting, is still going in the clear, even in TLS 1.3. So that's a leakage of activity. There was a huge debate about this on the mailing list, and interestingly, there was a draft, I think, the last week or the week before, trying to gather all those arguments together because there's such a strong body of desire to actually encrypt that SNI to hide activity. And a lot of this is born out of the fact that historically people would say, well, we don't need to worry about the SNI and the TLS handshake because you can see what people are looking up in their DNS queries. But the fact that there's been so much activity on encrypting DNS queries has actually driven the TLS folks to really focus their minds and saying, oh, hang on, if the DNS gets secured, we're left being the big leak of the server name. So this is about part of a concerted effort working together on the multiple places where information leaks across the internet. So I'll start by just really talking about privacy activity, and I want to talk about the IETF and what they've done in terms of all the general protocols, not just DNS. So the IETF was well aware that this is a problem for many years, and in 2011 they started work on a document, and the goal of the document was to tell protocol designers how to build privacy into the designs of their protocols to maximise protection and mitigate attacks. And it's the IETF. They took 2 years to get a document out. That's what happens. And the very month before they published it, a chap you've probably heard of called Edward Snowden leaked a few documents and revealed what the NSA had been up to, including mass surveillance of DNS. So what had been up to that point a really rather theoretical exercise suddenly became scarily real in that all these weaknesses in the protocols were being directly exploited to perform mass surveillance. So the IETF bounced right back, and only a year later, came out with another document saying very decisively and clearly, pervasive monitoring is an attack, in that pervasive monitoring is an attack not only on internet users, but also on organisations that rely on the internet. And they went one step further and they said that from this point forward, pervasive monitoring needs to be mitigated via the design of protocols to make this way, way harder for people. So this was a very strong statement coming out to say that, you know, encryption was absolutely necessary for the internet to function correctly. So why wasn't DNS encrypted? Why wasn't it already encrypted? Okay, well, what you need to do is take yourself back. I mean, we're all DNS folks. Think about 30 years ago when the DNS was actually designed. At that point in time, we really had no understanding of what the internet was going to become. And the driving forces behind the DNS design was availability, redundancy, and speed. Another thing about the DNS is that in privacy terms, it's what's called an enabler. It allows you to access other services. And so it's often not regarded as a service in and of itself. It's just a conduit to get you to a website or to a Jabber room or something like that. So as we know, the standards always said, use UDP first. It wasn't actually until 2010 it became mandatory to even implement TCP in a DNS server, and then it was only used for fallback. But still, both of these protocols are clear text. So anybody who wanted to look at your DNS activity could just sniff the network and see what you were doing. Additionally, there's been a long-held perception that the DNS is public. Data in zones is public, right? It's not personal, it's not sensitive. Why would we encrypt it? Why do we need to protect it? And I'll come back to that question later. So here's a basic example of how the original design of DNS didn't take privacy into account. This is how DNS works. We all know this. The stub sends the full query to the recurser, and the recurser goes off and sends the full query up to every single authoritative it talks to. And the schoolboy error here is that that's data leakage. The people running the route don't strictly need to know what your full query is, because you're an individual trying to make a query, and people who don't need to know that are discovering it through the design of the DNS. Now you might go, yeah, so what? The thing is, this problem gets a lot worse when you look back at the introduction of eDNS 0. So eDNS 0 was a much needed extension mechanism for DNS, and the idea was to tag a bit of extra data onto the DNS message where we could do really useful things like capability signaling, for example, or flag what the size of the MTU was. The problem was this was such a flexible mechanism that allowed people to use it using non-standard options to embed all sorts of things in the DNS messages. And originally, this was kind of done by service providers to provide more service, so it was a noble idea. So the kind of things that this was used for was ISPs used this as a relatively easy way to implement parental filtering, either on a per device or a per user basis. CDNs also decided to use it so that they could geolocate end users, send them to their closest server so that when they're browsing the internet, they got their cat videos without them buffering. It's a great idea, right? That's what we all want. The problem was with how they implemented this. In the case of parental filtering, it's been observed that rather than putting some logic on your home router, what your ISP will do is it will use the eDNS 0 option, and it will tag every single DNS query going in clear text up to the recurser with some identifier. If you're lucky, the implementation uses something like a hash of some sort of ID for you. If you're not lucky and your ISP was lazy, they'll do things like stick your MAC address in there, or your username, or a variety of things that really allow you to be identified. So there can be multiple people behind this router, and yet you can fingerprint the individual's traffic because it's exposed through the eDNS mechanism. It's similar but not as bad between recursive and authoritative. What the CDNs did is they decided to tag those queries, I'll say again, the queries going clear text over the internet, with the subnet that they came from. So it's not the IP address, but it's not far off, and it still allows people looking at that network connection or running authoritative servers to gather information about where the queries are coming from. You might think that DNS is a really rather anonymous protocol, but it isn't. You're behind a NAT, and depending on what's going on in your home router, you still might not have anonymity there. And even when you're behind a recursor, you might not have anonymity because your queries are being tagged. So people looking at this can associate personally with individuals identification information like, where are you this weekend? What are you doing? What do you look at when you get bored? So the other thing to reiterate about this is that these queries, which are getting tagged with all this information, the DNS isn't just for name lookups. We know that. More and more services are going into the DNS. So we've got MX records, which reveal the email domains which you want to send mail to, SRV records for the variety of services you might want to look up, OpenPGP, which is a great thing. However, it leaks the entire email address of the individual that you want to contact. And the problem is this is really only going to get worse. More and more is being put in the DNS. So I hope I now have your spidey senses tingling to the fact that your DNS activity can reveal a huge amount about you personally because of these implementation details and because it's being used for more services. So that's the picture in terms of what's going over the wire. I want to revisit this question of who's running these servers and what is happening to the data. So when you're thinking about the operator or whomever is running your recursor, you have to think about who has direct access to that data. Is it just your ISP? Depending on what country you live in, is it government, security services? What does your ISP do with your data? Do they sell it off? Look at what's happening in America with regard to net neutrality. You know, and do they sell it? Do they anonymize it at all? Or is it just raw data being sold? Also, how safe is this data? If your ISP isn't doing its job in protecting it, there could be breaches, and that will reveal the whole set of data that's being kept about you. And of course, these concerns change with your environment. It's one thing when you're at home with an ISP that you kind of trust and you've signed up to. It's another thing when you're out at a coffee shop using your phone on any old Wi-Fi, or you just don't know where you are. People are still looking and logging at DNS queries. And all these concerns, as I mentioned, extend up to the root because very often traffic is tagged going up there. So really what we're talking about with DNS, it's not a service, but it is leaking metadata. And because there's a potential to identify with individuals, what's been seen and proven through research is this allows fingerprinting of individuals' activity. It turns out to be really quite scary to see how individual your DNS activity is and how research with a not particularly sophisticated algorithm can identify an individual just because of the sites that you commonly visit and the pattern that you use in terms of how you do your lookups. And what this allows also is re-identification of individuals as they move across networks. So whether you're using your phone or your laptop, this pattern can be specific enough to identify you across different networks and devices. Beyond that, there's also been work to say, okay, encrypt your DNS. How far does that get you in terms of privacy? And there's some very interesting research that's shown that if an attacker has enough visibility downstream and upstream of a recursive server, even if the traffic between the stub and the recursor is encrypted, that isn't enough to completely obscure what's going on. Because DNS traffic is so characteristic in terms of message size and response size and timing, you can still identify a huge amount about what individuals are doing even when it's encrypted. And that's what's led to the desire to have a very, very solid grounding in how we pad queries to obfuscate this, and that will be talked about later today. As I mentioned, your operators are seeing and logging queries as well. So these are different ways data leaks out of the DNS. So if you're under the impression you weren't exposing your activity by using the DNS, well, we're really not in Kansas anymore because it's happening. So this is a risk matrix trying to summarize the main areas of problems. So we have problems in terms of both stub to recursive and recursive to authoritative, in terms of both passive and active monitoring. And we also have problems with what's being done with the data when it's at rest. So to move on from all the problem side, let's talk about what work has been done to try and mitigate this. I mentioned the majority of this work has come through the DPRIVE working group at IETF in terms of revising standards and creating new ones. So dPRIVE was created in 2014, and this was very much under the context of the Snowden revelations and the IETF realising it had to mitigate pervasive monitoring through protocol design. However, the dPRIVE working group started by going, this is a big, big problem. Like, we can't solve this overnight. There's a huge amount of work to do here. So the first thing they did was reduce their charter and say, we are going to focus on the stub to recursive problem initially. And the reason was they really didn't think that they could come up with a broad solution in one step. The stub to recursive reveals the most information. And also the recursive to authoritative is a particularly hard problem. And this comes down to how you would do authentication in that context. So you have relatively few recursives that you interact with. I mean, it might be, you know, it's in the tens, even if you count of every coffee shop and hotel you go to. It's a one to few relationship. However, the relationship between a recursive server and the authoritatives is huge. I mean, that's one to as many authoritative as you need to talk to get the answer you need. So setting up a flexible authentication mechanism which can work in that second context is much more of a challenge. So the first piece of work that came out of dPRIVE was mentioned earlier, which was work done by Stefan Bortsmeier. He generated RFC 7626, which is a problem statement, and it does an excellent job. It does a much more thorough job than I've just done of walking through the DNS ecosystem and identifying every point at which data leakage occurs. So I highly recommend it as reading. And in this document, it did one very important thing, is it went back to that question of the alleged public nature of DNS. And the argument the document puts forward is that whilst the data in the DNS may be public, an individual transaction with the DNS is not and should not be public. And the analogy it uses is that, for example, the website of Alcoholics Anonymous is public. It's a public website, anyone can read it. The fact that you as an individual visited that website is not and should not be in the public domain. That isn't public data. So having got a grasp on the problem, the working group turned to thinking about solutions. And the working group actually spent quite a long time trying to figure out what was the correct mechanism to use to do the encryption. The original proposal was actually to do Start TLS because it was fueled by the idea that we wouldn't be able to get a new port. This was back in 2015. So it's not ideal, but it could have run on port 53. Several people took an opposite view and said, no, this is a great use case. We should get a new port for it. And if we do, it makes life simpler and it makes it more robust because we can do TLS and DTLS. Now, of course, DTLS sounds like the natural choice here because DNS runs over UDP. Why don't we do DTLS? There are a range of arguments back and forth about this, but one that really came into play was the fact that DTLS suffers from the same problem that UDP does in that it has a path MTU limit. So it can't function as a completely standalone solution. If you went with DTLS as your primary solution, you would still have to implement TLS as a fallback mechanism. And of course, TLS is even more expensive than fallback to TCP. So the decision was actually to move forward working with TLS as a standard, and that became an RFC standards track. And DTLS is also an RFC, but it's an experimental status. So the idea was really, well, if we're going to do this, let's do it with TLS and let's do it right, and let's learn from what the HTTPS world has done in terms of TLS. So after making that decision, there's a bit of a to-do list. There's this getting a new port question. There's realizing the fact that DNS implementations are historically incredibly bad at implementing TCP. They tend to do, they did the minimum they had to fulfill the requirement to do fallback. We also have a really nasty problem with DNS, which is a bootstrap one, which is that normally when you want to connect to a DNS server, all you have is an IP address, and that isn't sufficient to be able to authenticate the far end. So that also needed tackling. And as I mentioned, we needed to deal with traffic size analysis. So it actually turned out to be really rather easy to get a new port. IANA were very receptive to this, and in October 2015, port 853 was assigned for DTLS and TLS to both run over that port. As I mentioned, we need to think about how DNS over TCP and TLS works. If you look at clients historically, they tended to do one-shot TCP, as I mentioned this morning. Open a connection, send one message, close it. So that had to be addressed. Even worse was what was happening at DNS servers in terms of their capabilities. They had incredibly basic TNS capabilities. Many implementations, for example, had hard limits of 10 or 20 TCP connections and hard-coded timeouts. So you could actually trivially DOS their TCP service with like a 3-line bash script. It didn't suffer because people didn't want to attack it, but that was the nature of the implementation. And there was no attention paid to tuning, optimizing kernels for TCP, to robustness. And a lot of people looked at performance measurements, which were done based on one-shot TCP, and just said, well, it's an order of magnitude worse, it will never compete, we're not even going to look at it. And there's some argument for that. However, what happened after the decision to use TLS is that there was a big effort to revisit the DNS over TLS standards. So work was done to say, actually, there's things like TCP fast open, and that allows you to put data in the SYN packet of a TCP handshake, so you save one round trip. And this is really now quite widely implemented. There's techniques like TLS session resumption, which get you up and running faster when you resume. And of course, as you heard this morning, TLS 1.3, one of its major goals is to reduce latency and look at 0 and 1 RTT setup. So because it's in demand in the HTTPS world, TCP and TLS latency is now a big thing, and people like Google are expending energy to reduce this. So we can piggyback on that. There was also a major effort to do a BIS to RFC 5966. So 5966 was the document in 2010 that actually said it's not optional to implement TCP, it's mandatory. 7766 kind of went back and went, actually it's mandatory to do it well. Don't do this one-shot stuff. You know, open connections, pipeline your queries, accept responses out of order, get it right, do it as it should be done. And also, there was a new standard allowing signaling from a client to a server to say, I want to keep my TCP connections open, give me a keep alive timeout. So there's a huge amount here that we can piggyback on. We're not the first people to try and do this, so there's the opportunity to take advantage of everything that's out there. I think I presented something like that this morning, so I will skip over and talk about authentication. Now, we'd love to be able to flip the switch and say, if we're going to do encrypted DNS, everybody should authenticate the far end. Just think about the confusion that came out with HTTP, HTTPS, how users struggled with it. Unfortunately, that's not a realistic goal. So what the standards are proposing are two ways to do DNS over TLS. One is called strict. And strict is for people who care more about their DNS privacy than they do about their DNS service. For example, if you happen to be in a country where you're being heavily surveilled, compromised, you're a journalist or an activist, and actually you really, really want to protect your DNS queries, then do strict. So this is, unless I can encrypt and authenticate my connection, I just won't do it. The far more pragmatic approach, and one which we expect to play a really key role during rollout of this as we sort of ramp up services, is something called opportunistic. And this is try and order. Your first thing that you try is to encrypt and authenticate. However, if you can't authenticate the far end for some reason, you're willing to fall back to just an encrypted connection. And the reason is that that at least gives you protection against passive monitoring on the wire. And then only if all of those fail to all of the servers you have available, you're willing to fall back to clear text. And that's because you want DNS service, and in some senses the argument is that's what you're doing today. So what we would like to see is a migration from using opportunistic to get rollout underway, and eventually in some utopian future, everybody doing DNS using a strict profile. Now, it does complicate things to have to authenticate the far end. Today, you just need an IP address to be able to connect to your recursive. But if you want to authenticate it, then you need at least one other piece of information to be able to do that. So the draft that's going through the IETF at the moment proposes using either an authentication domain name, which is easier to configure, more human recognizable, or an SPKI pin set, which is a bit harder to manage, but does have some nice properties with it. And of course, that's one thing, but we're DNS folks. Didn't we come up with this whole Dane idea? Shouldn't we be drinking our own champagne in that respect? Well, yes, of course we should. So the spec also includes a description of how to do authentication using Pure Dane. And as I mentioned this morning, also this chain extension. So I'll quickly run through the difference between the two. So this is a DNS client, and this is a DNSSEC validating client connecting to a privacy server using traditional Dane. So it would have some configuration information. It would go off and opportunistically do lookups for Dane records. It can get them and it can cache them. Then it does the TLS connection to the privacy server, and it uses the Dane records that it already has to authenticate that the server is who it says it is, and off you go. Everybody's happy. The chain extension works slightly differently. In this case, you still need to pre-configure your client. However, you know you're going to be talking to a DNS privacy server, so that server has its own Dane records available. In the client hello, the client signals that it understands this new extension, and the server then says, here's my server hello, and here's all my Dane records. The client can then authenticate them and proceed with sending DNS queries over this connection. And it reduces the latency on the setup, and it eliminates the need for an intermediate recursive to get the Dane records from. So in terms of where we are in solution documents that have come directly from dprive, and again, this is just stub to recursive, we have DNS over TLS as a standard. We have an eDNS zero padding option, which allows us to hide the size of the queries. And I particularly like this one because it feels like we've claimed back that eDNS option from the dark side. You know, it was being used to expose information, now we're using it to pad queries. So that's a nice thing. And we also have DNS over TLS as an experimental standard, and we have a draft which is in IESG last call to describe authentication. So the specification picture is really doing quite well after 3 years' work from this group. Of course, the next step is a much bigger one, is to try and tackle the resolver to authoritative link. There's a draft, again, by Stefan Bortsma, proposing some options, which is interesting and still needs, I think, to gain a bit of momentum. Although in Prague in a couple of weeks, I believe on the agenda is a discussion to talk about rechartering dprive specifically to look at recursive to authoritative, which would be a good thing. And also it's being asked for data on DNS over DTLS to feed into this whole discussion. So that's still active work. Okay, so I want to give a tour of some other work that's been done outside dprive now. So I mentioned this problem earlier with the leakage, and again, more work involving Stefan Bortsma. He's been very busy. He was involved in RFC 7816, which came up with the idea of QName minimization, which says, only send the part of the query you really need to the authoritative who can give you the answer for it. And this looks really kind of obvious, and a kind of, well, why didn't we do it this way first time round? And the answer is, it really isn't as simple as it looks. There are some really, really fiddly corner cases that you have to handle if you do this. And interestingly, some of those were figured out at the time that the draft was progressed through the working group, and a bunch more came to light during implementation. I know particularly colleagues of Willems found that they were fighting all sorts of corner cases with this, so it's not such a trivial thing, but we now have multiple implementations of it, and it's being used quite widely. One area where I really, really think we need more work is in terms of data handling. And the thing about this work is, for us, for many of us, is the solutions here aren't purely technical. They're about politics and they're about policy. So one example is a straw poll. How many people here have read the contract they signed with their ISP and knows whether or not their ISP sells their DNS data to advertisers, for example, to target you? Yeah, I'd be impressed if anybody had. So, yeah, I did because I knew I was going to ask the question. So it's not just at the ISP level, it's actually at governmental level. There's policy and then there's practice. And I mean, I come from a country where we have what's called the Snoopers Charter, which the government passed with spectacularly vague wording to allow them to get your browsing history, which some people think limits it to HTTP. I think you'd have a tough time arguing that that excluded them having access to your DNS data. There's also a lot of tension here at the moment, which we as technologists can't resolve. So we have multiple governments demanding backdoors and encryption for security purposes, and yet we have reports from UN rapporteurs and from the European Human Rights Council saying we absolutely need encryption to protect human rights. And so there's a real conflict here, and it isn't clear to me yet where that is going and how it will be resolved. What we can probably more tangibly do is try and fight for transparency from providers on what they do with our data and making them fess up when they have a breach, not 3 years later, but the day after it happens or very soon after it happens. We also need to think about methods for de-identification of data. There are good use cases for things like passive DNS to share data for research and for security analysis, but we need to be sure that we protect individuals when we share that data, and that's an emerging field at the moment. So this is where we need to do much more work. There's a whole bunch of really interesting work coming out at the moment about doing DNS over HTTPS as well. You may not be aware of it, but I think it was in 2015, kind of quietly and really rather out of the blue, Google announced that they had a DNS over HTTPS service. It uses a completely non-standard protocol. When these slides are available, that's a link to their API page. You can go and play with it yourself. They have a nice little GUI. It's really not quite clear where they're going with this. On the standard side, things are very much in flux and have been for a few years. Ideas have come and gone. The two that seem to be stabilizing now are, one is using HTTP in order to tunnel your DNS queries over it. So you kind of embed them in wire format and tunnel them through. There are implementations that exist. There are servers that offer this. One of the things that this lets you do, of course, is if somebody is trying to block you doing encrypted DNS by just blocking port 853, you can do this over 443, and they'd have to block your HTTP as well if they want to defeat you using this mechanism. Very recently at the ITF, there's been some work regarding how you could actually mix DNS queries in with HTTP2 on the same connection. So the idea is that HTTP2 uses a set number of streams on a connection, and you can have additional streams that you could run your DNS queries over. Now this would mean that you get your DNS service from whomever you made the connection to, but there are very big players like Google and Facebook who are very interested in serving your DNS under these circumstances. And this provides even further obfuscation, because there's an argument to say if you're doing pure DNS over a connection, somebody could still figure that out and attempt to block it. Whereas if it is completely mixed in with your HTTP, it's a different game. They really, really can't see what you're doing there. What bubbled up at about the same time is talk about doing DNS over QUIC. How many people in this room are familiar with what QUIC is as a protocol? Okay, we've got a handful. Okay, I'll skim it very quickly then. QUIC's really interesting, I think. It was originally developed by Google, and they did it as a proprietary development because they're Google and they can, so they just invented a new protocol. It runs over UDP, but it's much more like doing HTTP2 HTTPS2 on top of UDP. It mixes and matches transport properties. The last statistics I heard were that 35% of Google's egress traffic uses QUIC. So basically, from Chrome up to Google servers, it's QUIC. You can see it in Wireshark if you just fire it up. You can see how much of it is going that way. So that's 7% of the entire traffic on the internet is using QUIC, and loads of people have never heard of it. They spent 2 or 3 years developing it and got it to a point where they thought it was mature enough that they did want to standardise it. So they've taken it back to the ITF. An ITF quick working group has been developed. And this is a really interesting thing to watch because you have a tension between network folks who, so Quick by its nature encrypts a lot, including headers. So network folk aren't particularly keen because they want to be able to inspect traffic. Google want it to still serve their purposes, and the ITF is the ITF. They want to argue for years about how it should work. So I think watching that progress will be really interesting. In terms of using it for DNS, the boxes it ticks are, although it runs over UDP, it's reliable, it's got all that built in. It's low latency, just like TLS 1.3, very similarly, so it should be performant. One of the nice things it gives over UDP is it has increased source validation, source address validation, which is of course great for mitigating DDoS. And of course it doesn't suffer from this pesky MTU limit, and you can send queries however big you want almost over Quick. But the killer feature obviously for privacy is it's encrypted. And when I say it's encrypted, I mean it's encrypted. There is no unencrypted Quick. It's not like HTTP where there are two flavors. So switching to doing DNS over Quick is a really attractive is really attractive in the long term for privacy. So to come back to that matrix I presented earlier and talk about how we're mitigating those problems. So we can encrypt between the stub to the recursive. We can authenticate to mitigate against active attacks. On the recursive to authoritative, we have some mitigation in the form of QName minimization, and there's still a bunch of work to do in terms of best practices. Okay, how am I doing for time? Yep, okay. I'm just going to very quickly talk about service discovery, but I won't spend long on it. Service discovery is another aspect of DNS that is really used to advertise services, and very often people think it's only about local services, but the leakage involved in service discovery can be global because it can send queries out beyond your local network. Very often it's used to advertise services. You know, you want to share photos, you might want to be able to connect your phone and your laptop, so you have them advertise services back and forth. But of course, just look at the amount of personal information you've just leaked by doing this. You've leaked your name. By default, certain OSs will give the laptop the name of the user when they advertise the service. So, and anybody looking at this will know they can look around a room and go, who's the person with the phone, the laptop, etc. Oh, that's Alice over there. And again, there's lots of research to say when you advertise services in these ways, you not only advertise the name, the devices, the services, inside each of those advertisements, you can go right down to particular attributes of these services to the point at which knowledgeable people can actually identify the kind of device that is advertising the service, right down to the hardware. So this is another source of a place where even technical people might be oblivious to the fact that they're leaking information about what they're doing through the DNS. But there is a working group, DNSSD, and they're on the case looking at a whole range of solutions for this as well. Okay. So now we'll move on, having talked about standards and the evolution there, to talking about where we are in terms of implementing and deploying this. So one place I want to draw your attention to is a site called dnsprivacy.org, and this is the homepage of the DNS Privacy Project. So I'm involved in this, NLNet Labs are involved in it, Salesforce are contributing, Stefan's done a huge amount of work to help out. We've had grants from NLNet Foundation, a whole range of people are involved in this. And the idea was to create a central point of reference for information about how to do DNS privacy, what's available, what's the state of the standards, that sort of thing. One thing we do there is we try and track in the most common open source resolvers, what are the state of implementation of the standards. So I will say I've just picked 3 here for simplicity in the slide. Other name server implementations are available. But you can see here that Not Resolver is probably the most fully featured today in terms of doing DNS over TLS. Unbound isn't far behind. Bind has chosen not to implement TLS. I mean, it's a common concern among a lot of implementers, which they don't want to link to OpenSSL, which is the obvious choice as a TLS library. And instead, what's being recommended in that case is, rather than having an implementation native inside the name server, is to use some sort of TLS load balancer, some sort of proxy to actually handle the TLS load for you. So on the dnsprivacy.org site, we have guides for how to configure Nginx or HA proxy to do this. Bind, on their knowledge database, actually have something which shows you how to do it with S-Tunnel. There are a few disadvantages to this, though, because you don't have a true DNS load balancer there. So what a lot of folks would like to see is something like DNS Dist implementing TLS to provide the combination of all the hugely powerful features it has for doing DNS load balancing with taking all the TLS load. So it's not there yet, but I've heard very good and encouraging news today about where it is. So I'm very hopeful that if that emerges, it will be a game changer in terms of facilitating people running DNS over TLS servers. On the client side, as you heard this morning, there's been a lot of effort on GetDNS and Stubby to make that Rogo completely green. That's what we're aiming for in terms of having fully featured stub to do privacy. KDIG, which is the not resolver tool, is doing pretty well as well. And Bind, again, has some of the TCP features, but not TLS. So what we've seen over the last few years is an increasing take-up in implementations of better DNS over TCP. QNAME minimization is looking pretty healthy in terms of implementation. We have a good few implementations of DNS over TLS. DNS over DTLS really hasn't seen any implementation. And I'm not really sure why that is. People seem to be thinking if we're getting TLS right enough, that it's simpler just to have one solution. And as I mentioned, DNS over HTTP is also out there in the wild. BII has an implementation. So how much of this is actually running, though? So another thing we do on the dnsprivacy.org site is we are keeping a list of what's available at the moment. And in terms of recursive servers, we have a set of experimental servers. There was 10 when I sent the slide in. There are now 11. It will be updated very shortly with another new one. And people running them are people like NLNetLab, Synodon in conjunction with SurfNet, and Censored DNS, which is a really nice service out of Denmark. And Daniel Kahn-Gilmore from the ACLU is running Not Resolver. So we have a little dashboard on the website where we're trying to monitor these servers. They're all experimental, so we do see them going up and down all the time, actually, because they're coming across problems. But this site should tell you which ones are up, which ones you can authenticate to with the information available on our site. We're trying to flag when they're having certificate expiries, because we've already seen 2 or 3 of them run into this problem, because DNS server folks aren't used to having to think about certificates and renewing them. So hopefully this will mitigate that a little bit. And we're trying to show which ones use QNAME minimization, and the ones that don't are really only doing it because they're using Bind and it's not in the latest version of Bind. So there are servers out there you can use if you want to. I'll come back to what I was talking about this morning. This is where Stubby fits into the privacy picture. So you need some client software to enable people to choose to do this if they want to. So it's a privacy-enabling stub resolver. There is a user guide available on the GetDNS website. I'll give you a heads up that some of this is about to change, because at the moment Stubby is integrated very heavily with GetDNS. We're about to break it out to be a standalone application, and that'll probably happen in the next week or 2. As I said this morning, it runs as a daemon, picks up your queries, and it points at this set of experimental servers. The command line tool is still very much a prototype, but we're working on this UE, and it's definitely prototype stage, as you saw. We're interested in people who've got strong views on how UEs like this should work, what level of interaction we should be having. Which brings me on to another question to do with deployment of DNS over TLS, which is about the usability of this new paradigm of wanting to do private DNS. So when you think about it, DNS privacy is a completely new paradigm for end users. Most non-technical end users don't even know what the DNS is. Occasionally it breaks and they get some stupid message and they're like, what's the DNS? It's not working. But But most of them have no idea. I mean, think about how much users struggle just with the difference between HTTP and HTTPS, and that's presented graphically, beautifully with little locks and stuff. And yet people like Google and Firefox are constantly redesigning their interfaces because they're finding people are stumbling again and again and visiting insecure websites. So we need to tackle that side of it. We need to explain to end users what the problem is and how they can use it securely. One hurdle there is that DNS folks, they're not used to these end user folks either. We're used to everything happening under the hood and not worrying about what they think or what they know. So there's a whole new process we're going to have to go through in terms of working out how to make these GUIs usable, these choices usable, or how to integrate them into end systems. So to summarize, I just want to talk about what I think the key challenges are in the short term with this project. I think the first one is awareness, both among technical communities and non-technical communities. That's still an ongoing issue. I really think we need to look at, on the client side, getting DNS over TLS enabled stubs integrated tightly into OSs. So as well as having Stubby running as a daemon, a project we're looking at is a dbus interface to get DNS, so it could be a drop-in replacement for System D, for example. So there's a whole range of solutions that we need to be actively looking at to get things enabled on client end machines. We clearly need increased deployment of servers. We only have experimental ones at the moment. I'm aware of at least 2 organisations who have expressed the desire to do Anycast deployments before the end of the year using DNS over TLS. So I think when that happens, it'll be really interesting. I pester the Google folks every single time I see them. When are you going to do it? And they tell me, oh, it's really important. Yeah, it's on our to-do list, but it's not next on the to-do list. So, you know, I'm very hopeful that could still happen, or a similar player out there do it. As I've mentioned, more transparency in data handling, and we have the recursive to authoritative problem to solve. So to summarise where we are today, DNS privacy is a real problem. It really is leaking information about individuals' activity on the internet. It's a really big solution space. It's not something we can solve overnight, but we've made really good progress in the last few years. There are today things you can do. If you really want to protect your DNS, you can grab Stubby. I had it running on my machine. When I travel, I normally have Stubby running because I don't know where I am. I run across some really interesting cases where port 853 is blocked. I was trying to give a demo yesterday of Stubby, and not only was port 853 blocked, I couldn't even do DNS over TCP on that network. They had blocked that too. So there are still challenges, and I think in those cases, port 443 is your friend. But there are some solutions you can use, and there are servers out there, and I definitely think we'll see a lot of movement in the space in the next year or 2 in terms of increasing services and increasing access to end users being able to do this. Okay, so I think I've still got a bit of time for questions, so I'd like to thank you for your time, and I'll take any questions.
Okay. Do you have some questions?
Je vais faire la question en français et en anglais. Concernant l'application des personnes au projet DNS Privacy, vous avez mentionné donc Synodon, Salesforce. Est-ce qu'il y a des institutions publiques ou des organisations génériques qui sont concernées par le sujet de la protection des données, qui participent au projet ou qui ont des intentions de participer au projet? So you mentioned Salesforce, Synodon, and NetLabs, of course. Do you have any declaration of intention to contribute, like with grant or contribution from public institution or organization into the DNS privacy project?
Yes, so I have a couple of grants in, which I can't yet speak about because they're not confirmed, but they're sort of large foundations interested in open internet. They're now recognising that this is something that they can contribute to and make a difference to. So hopefully I'll be able to announce one very shortly on the site.
Okay, other questions? Yes.
Merci, je vais faire la même chose alors en français et en anglais. Vous avez porté votre argumentaire sur la nécessité d'encryption du DNS, sur le risque de filtrage des données en clair. Et j'aimerais, au-delà de ça, savoir si vous avez des cas concrets de scénarios où la donnée elle-même a été abusée. La distinction que j'essaie de faire, c'est que la même chose pour HTTP, c'est mal de laisser en clair des données HTTP. Par contre, j'ai moi un exemple concret. Lorsque j'ai utilisé HTTP en clair, on m'a piqué mon numéro de carte de crédit. Donc, est-ce que vous avez des cas concrets d'abus des données? So I'll try to do that in English.
Thank you. I'll need that.
And thanks for the presentation. You put the case for DNS encryption on the basis of the fact that leaking public data is bad. I was wondering whether beyond that you had concrete examples, maybe other than state surveillance, which is indeed an issue, but whereby DNS data has been abused. And the difference I'm trying to make is that indeed, like for HTTP, it's very bad to use that with public data. However, I have a concrete example where my connection has been sniffed and my credit card number has been nicked. So there's a slight difference between those two things. So I was wondering whether you had examples of such cases. Thank you.
I don't have concrete examples, but there's a lot of anecdotal evidence to argue that people like insurance firms are very interested in looking at your DNS data and inferring things about you. Now, whether they go so far as to do undercover surveillance, I don't know. But the fact that it's the potential risk that's there, and not necessarily from companies who would do that themselves, but from malicious parties who would do this and then sell the data on. So one thing that's pointed out to me is that although your operators are seeing your queries, there's a route for bad guys to try and sniff this and then sell it on because it does have monetary value. So I don't think I can give you rock solid examples of that happening, but the fact that this data is inherently exposed in clear text in a way it isn't in any other protocol is really what we're trying to mitigate here. So, and just take away the possibility of doing that. Okay.
Okay, other questions? Yes?
Neil O'Reilly. Sarah, a few slides back, you had a mark down in the corner that said help wanted or help needed.
Yes.
Would you like to say a little bit more about what kind of help you're looking for, who can help? Is there something I can do at home on my home network to validate some of what you're doing, or is it mainly bigger organizations that you're looking to for help?
So we're looking for individuals to do testing, obviously, because there's been some research into blocking of port 853, which it was done a couple of years ago, but it showed it was relatively minimal. Of course, if we run into that in domestic situations, ISPs routinely blocking it, then that's an issue that we need to deal with, and it may cause a real change. I mean, that's the kind of case where you start really thinking about port 443 is where you go with it. So any and all information in that regard is useful. We think we have a reasonable set of experimental servers, and I think on the server side, the next big step has to come from an operator. And I think these Anycast deployments will be the really big difference. The other place is in terms of putting pressure on OSs to be more flexible in terms of their DNS capabilities that they offer and how they allow other stubs to integrate into them. But again, that's an organisational issue as well. So as individuals, probably the most important thing I would do is ask you to get involved in this to protect yourself at this stage. Think about protecting your queries. When you start thinking about how exposed these queries are, every time you go to a new hotel or get on a new Wi-Fi, you suddenly start thinking, or you click that little box saying you accept our terms and conditions. These people are using your DNS to track you, to sell you things, to spam you. So it's not like Privacy Badger. It's not yet at that scale, which is a nice little plugin you can get to stop ads tracking you. But one thing I do notice with this is that as you're moving around environments that you might call untrusted, this at least gives you some level of protection that you're not exposing yourselves in those environments.
Is there any current cooperation with legal specialists, especially in the GDPR area? And if so, is it a kind of help also, whether it is by mandate or whatever kind of solution, as a leverage to push for these solutions?
So that's another area that we did spend a little bit of time talking to RIPE about this, but it didn't come to fruition because they seem like the right body in terms of a Europe-wide perspective, absolutely. So that's something we certainly want to revisit with them in terms of what can we do to raise awareness and put pressure on countries with regard to this. So that's certainly another non-technical but crucial part of this. If we don't have that, then the technical stuff can fall. So yes, thank you. Great.
Okay, more questions? So I have just a question about middle boxes, because it's you already talk about that, but internet is not so end-to-end, and you have things in the middle that blocks deployment of new protocols. For example, DCCP and PTCP have a lot of problem to deal with that. So is it the case for privacy with DNS, or you can?
So we haven't seen that yet, but I think that could really change as we see deployment scale. I mean, that's where we would really discover, I think, some of these problems. As I said, the bit of research that's been done has said they're pretty lenient at the moment with allowing this stuff through. But when people realise what this traffic is being used for, then who knows what they might do in terms of blocking it. It's one of the reasons why QUIC is such an attractive prospect for the future, because blocking QUIC will probably not be an option. So, you know, utilising that aspect of it would be really nice.
Okay, thank you. So I would like to thank you a lot, because you have to rearrange your agenda to come today for this very nice tutorial this morning. And this
My pleasure. Thank you for inviting me.
Thank you very much.